Hello again, oceanography students. So for the second video for tides, we're going to talk about how the tide changes over the course of a day and over the course of, well, we kind of already talked about how it changes over the course of the day, but we'll talk about how it changes over the course of the month and how it changes over the course of a year. We'll talk about the currents that are created by tides, and we'll talk about some other interesting phenomena as well. Okay, so how do the tides change over the course of a month? So first we need to know the definition of the distance between a high and a low tide. So we call this tidal range. Again, tidal range means the difference between the high tide and the successive low tide. So it's basically like how far away is the low tide from where the high tide hit the beach. Okay, so in this little image here, we have the Earth, and it's showing us the position of the moon around the Earth, and then you have the sun over here, right? So the moon, based on the position of the moon and the sun, we go through different moon phases. Okay, so when the sun and the moon are on opposite sides of the Earth, we would have a full moon. When the sun and the moon are on the same side, we have a new moon. When they're at right angles, we have a quarter moon or a three-quarter moon. Okay? So notice that, remember that the sun is also a big celestial body that is going to influence the tide. It just doesn't influence the tide as much as the moon does. So essentially what we have is we have a lunar tide and we have a solar tide. The solar tide is much smaller than the lunar tide is. So sometimes those two tides are creating bulges that are directly in line with each other. Sometimes they're creating bulges that are opposite from one another. Okay, so when they create bulges that are directly in line with each other, then we experience the greatest tidal range. That means we experience the highest high tides, and we would experience the lowest low tides. When the solar tide and the lunar tide are not in line with each other, we would, or in other words, when the moon and the sun and the earth create a right angle, like when there's a first quarter moon or a third quarter moon, the bulges that are created are opposing each other. Okay, and so what we would end up having is a high tide with the lunar bulge and a low tide with the solar bulge. So that means that the tidal range would be the smallest over the course of the month. That means that we would have a lower high tide and a higher low tide. And so what we call it when they are in line, when it's a full moon or a new moon, we call that a spring tide. This would be the greatest tidal range produced over the course of the month, right? And since that happens twice, we would have two spring tides over the course of the month. When the Earth, the moon, and the sun are at right angles, we call that a neap tide that gets created. So that means that we have, again, the smallest tidal range is the neap tide. And since that also occurs twice, when there's a first quarter moon or a third quarter moon, we have two neap tides that would occur over the course of the month. So we can look at a different image here to show that. So here's the sun, this represents the moon, and then you have the earth. And we have the two tides that are shown here. So we have a lunar tide, and we have a solar tide. And we can see the lunar tide is in light color, the solar tide is the darker blue. And you can see that the solar tide is much smaller than the lunar tide is. Again, that's because the moon is so much closer. It creates a greater gravitational pull on the earth than the sun does, even though the sun is much larger. Okay, so when all three are in line, then you have the solar tide and the lunar tide being in line as well. And so we have the high tide, the highest bulge created by the solar tide, the highest bulge created by the lunar tide are in line with each other. So now you have a very high tide. But then over here, because that's pulling so much water over, then you have a very low tide. That means you have a very large range in the tide over the course of that day. And again, that would happen 2 days over the course of the month. And that's called a spring tide. A neap tide is created when the solar tide and the lunar tide oppose each other. They're in opposite directions. Okay, so we see that the solar tide is created in the direction of the sun and also in the opposite direction, just like the lunar tide. Lunar tide is directed, but the lunar tide is created by the moon, right? So here's the moon in the same direction, and here's the moon in the opposite direction. So here, this lighter one again is the lunar tide, and this darker colored blue is the solar tide. Okay, so what we would experience on Earth is when we were under the bulge for the lunar tide, we would experience a high tide. When we were under the bulge for the solar tide, we would actually experience a low tide. Okay, and so that is what we would. The tidal range would be the smallest, right? Because it's still, you're going to see a higher low tide and a lower high tide. Okay, so the difference between the low tide and the high tide is going to be the smallest, and again we call that a neap tide. How does the tide change over the course of a year, right? So that's how it changes over the course of the month, but what about over the course of the year? So the Earth is orbiting the sun in what's called an elliptical pattern. So that means that sometimes the Earth is close to the sun and sometimes the Earth is farther from the sun. And so that's going to change depending on the time of the year. So when the Earth is closest to the sun, we call that perihelion, and that occurs in January when the Earth is 148.5 million kilometers away from the sun. And then in July, Earth is at the farthest position from the sun in its orbit, and we call that aphelion. So anytime there are two words that either designate something being near or far, the one that starts with the A always means that it's the far one. It's like A kind of represents without or far away. So aphelion would be Earth is far. Perihelion would be Earth is close. Okay, so again, Earth is closest to the sun in January. Earth is farthest from the sun in July. And therefore, we're going to have the greatest solar tide in January and the smallest solar tide in July, because remember, the distance is important. Okay, so tidal ranges are largest at perihelion and smallest at aphelion. But of course, it gets more complicated because we have to think about the moon's position as well. The moon also rotates around the Earth in an elliptical orbit, which again means that sometimes it's closer to the Earth and sometimes it's farther away. So when the moon is closest to the Earth, we call that perigee, which is 375,000 kilometers. In apogee, the moon is farthest from the Earth, and that is 405,800 kilometers. Okay, so again, closest is perigee, farthest is apogee. Okay, so the one that starts with A means farthest away. So that cycle from perigee to the next perigee occurs every 27.5 days. So again, we're going to see the largest tidal ranges during perigee, when the moon is closest to the Earth and has the greatest effect. So this shows you the orbit. So here's the sun, here's the Earth orbiting in this elliptical pattern. So sometimes the Earth is closest to the sun, and sometimes the Earth is farthest. It's closest in January and farthest in July. Then we zoom in on the Earth and we see that the moon kind of has that same orbiting pattern, where sometimes the moon is closer and sometimes the moon is farther. So in perigee, we call moon's closest, and apogee is when the moon is farthest. So I was wondering, what effect does the distance of the sun, the distance of the moon, and the moon's phases actually have on the tidal range where we live, so just down in Carquinez Strait? And which has the greatest effect, which has the least effect? So what I did is I went and I actually looked up the tidal cycles for specific days that had different characteristics of when the Earth was close and when the Earth was far from the sun, and when the Earth was close or far from the moon, and also the position of the moon, Earth, and the sun, so the moon's phases. And so the first question was, what is the effect of the sun's distance? So the effect of the sun's distance I determined by looking at a day in January when the Earth was in perihelion to the sun, right? So it's going to be closest. And I also looked up the phase being a quarter moon and the distance from the moon and the sun being an apogee. So the tidal range on that day was 4.28 feet. So again, that's the distance, the difference in the height of the high tide and the low tide. Okay, so then I compared that to a day in July when the Earth was in aphelion to the sun, right? So the Earth is farthest from the sun now, and I kept the other two variables the same. This day had a quarter moon and also was an apogee, meaning the moon was farthest away. The tidal range when the sun was farthest was 2.25 feet. Okay, so the change from when the Earth is closest to the sun versus the Earth being farthest from the sun was 2.03 feet. Okay, so a difference of 2 feet. So just remember that, 2 feet. Then I looked up the effect of the moon's distance. So this time I looked up a day when the Earth was in perigee to the moon, meaning it was closest to the moon, or the moon is closest to the Earth, I guess I should say. And then the other two variables I kept the same for the 2 days that I looked up. So I looked up a day in January when the moon was a quarter moon. Okay, and so I got this, and I could then calculate the tidal range by taking the difference between the high tide and then the low tide, and the difference was 6.98 feet. Then I compared it to a day also in January when the Earth is in perihelion to the sun and a quarter moon phase, but this time it was on a day in which the moon was farthest from the Earth over the course of that month, and so the moon was in apogee. The tidal range then, comparing the high tide to the next low tide, was 4.28 feet. So the moon's distance produced an effect of changing the tidal range 2.7 feet. All right, so the first one was about 2 feet with the sun. The moon's distance gives us about 2.7 feet. Okay, so clearly the distance between the Earth and the moon has a greater effect than the distance between the sun and the Earth. So finally, the last thing I looked up was the effect of the moon's phase. So this time I compared a day where there was a new moon, so that means the Earth, the moon, and the sun are all in line, and to a day where it was a quarter moon, meaning that the moon, the Earth, and the sun create a right angle. So that means that in this time, the solar tide and the lunar tide should be lined up, and at this time, the solar tide and the lunar tide should be opposite of each other. Okay, so what I got for a tidal range in a new moon was 7.44 feet, and what I got for a tidal range in a quarter moon was 4.28 feet. So that's a difference of 3.16 feet. Okay, so in order of ranking of which has the greatest effect, it would be the moon's phase seems to have the greatest effect, followed by the distance between the Earth and the moon, followed by the difference between the Earth and the sun. And so that's real data to show you that. Okay, so all areas don't experience semi-diurnal tidal patterns. In the tide charts here that I kept showing you, you see this, the line, the blue line, it rises and it falls and then it rises up again, but it's not rising as high the second time. Then it falls again and it's not falling as low the second time either, right? So this is not a semi-diurnal tide, because a semi-diurnal tide would rise, it would fall, it would rise back up to about the same height, it would fall back down to about the same height, and it would be doing the same thing every day. So why do we not experience a semi-diurnal tidal pattern? We actually experience what's called a mixed diurnal pattern. So remember that a tide is a wave. It has a very long wavelength, therefore it acts as a shallow water wave. Shallow water waves always touch the sea floor, right? So the depth of the water affects the shallow water wave. What else affects waves? Well, the shape of the coastline, remember we talked about that, and also the topography of the bottom. If there is canyon, or if there is a underwater seamount or anything like that, or how fast the shoreline drops off, and all of those things are going to affect the way that the tide travels. Thus, the pattern experienced in a given location depends on a number of factors that are specific to that location. So here is a map of the world that is showing you different tidal patterns around the world. Okay, so green represents the semi-diurnal tidal pattern, yellow represents diurnal tidal patterns, and mixed tides are represented by the orange. Okay, so here is the west coast of the United States. You can see that we're all in orange, which means a mixed tide. Over here on the east coast, they're all in green, so that means a semi-diurnal tide. And then in the Gulf of Mexico here, we see that that's yellow, so that would be a diurnal tide. Okay, and so a mixed tide is basically where you have two high tides and two low tides a day. However, the high tides differ in height from each other, and the low tides differ in height from each other. A diurnal tidal pattern actually just means that there is only one high tide and one low tide over the course of the entire day. Whereas a semi-diurnal tide has two high tides and two low tides, and the two high tides are the same height and the two low tides are the same height. So these charts are showing you 48 hours. That's why you're seeing more than two highs in the mixed in the semi-diurnal, and you're seeing more than one in the diurnal. It's really just one for the 24-hour period. For a diurnal, two high tides for a mixed tide for a 24-hour period, two low tides for that 24-hour period, and the two high tides differ in height, and the two low tides differ in height. And then again, semi-diurnal shows two highs and two lows that are about the same height. Okay, so three tidal patterns. You have the diurnal tidal pattern, which is one high and one low each lunar day, and we experience that in the Gulf of Mexico. We have a semi-diurnal tidal pattern, which is two high tides that are the same height and two low tides that are the same height per day. That we experience on the east coast of the United States. And then here we experience a mixed tidal pattern. That's two high tides of differing heights and two low tides of differing heights each day. And again, that occurs on the west coast of the United States. Okay, so again, here we have some tidal graphs that are showing you that. So again, semi-diurnal means you have two high tides that are about the same height and two low tides that are about the same height over the course of a tidal day, which would be a lunar day, right? Mixed tide, you also have two highs and two lows, but they differ in height. Diurnal, you only have one high and one low over the course of a tidal day. Okay. Now, when tides occur, they also create currents or movement of water horizontally. So when the tide is high or low, we actually call that slack tide, which means that there is no current. Okay, so right at high tide or right at low tide, there's no current created. But when the tide is changing, there is a current that gets created. So an ebb current is created when the tide is going out or moving away from the beach. So that would be going between a high tide and a low tide, you would have an ebb current. A flood current is when the tide is coming in. So that means that or in other words, the beach is being flooded. So that would happen after a low tide and before a high tide. Okay, basically transitioning from a low tide to a high tide is what creates the flood current. Okay, in an estuary like San Francisco Bay, instead of just having the tide, the current flooding the beach or moving away from the beach, we actually have water moving throughout the bay, filling in all of the space and rising along the shorelines as well. So essentially, what we have is, here we have the Pacific Ocean, and then we have San Francisco Bay. So the tide is going to come in from the Pacific Ocean into San Francisco Bay, and then it's going to spread out and create this current. Okay, so the water is not just rising as that's happening along the shoreline. We actually have water that is moving, creating a current that is moving in the direction that is coming from the Pacific Ocean and going in. And then when the tide would go back out, the current would be in the opposite direction, moving out. Okay, there are some other interesting things that occur due to tide. So a tidal bore, which is often referred to as a tidal wave, is a wall of water that moves up a narrow estuary river due to an incoming tide. So the term tidal wave is not correctly used when you're talking about tsunami, because obviously tsunami is not a tide, it's not a tidal wave, which we've already talked about, right? The tsunami is caused by a sudden geological event, most likely, right? Whereas the tide occurs because of gravity. Okay, so what happens with the tidal bore is that the river will always flow towards the ocean. Okay, so when a tide is coming into the river, you have basically two opposing forces, and that creates a wave. And that can create a wave that can have heights of up to 5 meters high. And of course, this is going to be the most drastic when there's a spring tide, right? When there's the biggest difference between a low tide and a high tide, because when a high tide comes in, then that means that there's a lot of water that's coming in and causing that. Then there are some places around the world, such as the Bay of Fundy, which experience extreme tides, which means you have very, very high tides and very, very low tides, which means you have like the most extreme tidal range. So the reason why it occurs in the Bay of Fundy is because so every body of water has a natural oscillation to it, meaning a natural sloshing back and forth of the water on a specific a specific period. Now, the natural oscillation in the Bay of Fundy is actually equal to the tidal period as well, and so they match up, and therefore the northern part of the bay narrows and shallows, and when that natural oscillation is matched up with the tidal oscillation, then you experience extreme high tides and extreme low tides. And of course, this is going to be the most obvious when you have a spring tide, when you have the largest amount of water coming in and the largest amount of water leaving. So the tidal range could be 2 meters in the open part of the bay, but when you go up into the more narrow arms, you see the more drastic change, and so the tidal range can actually be 17 meters. So the difference between a high tide on the shoreline and a low tide on the shoreline is 17 meters. That's a huge difference, and that would put boats that are in a harbor, that would be up in the water during high tide, it would put them on the seafloor in a low tide. And I'm going to post a couple of videos that you can watch to see these phenomena as well. Okay, so here's a picture that is that same scenario. So if you have questions, please post them under the weekly discussions, and I will see you in lab on Thursday.